All right, in this video, we're going to look at question 5, which deals with radial fields. So we're going to let the vector r denote the position vector for the point xyz in R3. So it's equal to xi plus yj plus zk. And we'll let the scalar r be the magnitude of this position vector. So it's the square root of x squared plus y squared plus z squared. Or put another way, it's just measuring the radial distance from the origin to the point xyz. And so our job here is to compute the divergence of this vector field r divided by various powers of its magnitude. Okay, so to help us do these calculations, we're first going to note that if you differentiate this quantity scalar r with respect to, say, x, well, you'll get 1 over 2 times the square root term, and then you're going to pick up a factor of 2x from the chain rule, because that's the x derivative of what's inside the square root. And so this simplifies to x divided by that square root term, which is just r itself. So it simplifies to x divided by r. Okay, and by a similar argument, the y derivative of r is y divided by r, and the z derivative of r is z divided by r. Okay, so I'm going to keep these in mind as we go through these calculations. So let's go ahead and do the first one here. This is the divergence of just the radial vector field r itself. So its components are just x, y, z. So to compute the divergence, I'm going to take the x derivative of x, which is 1, the y derivative of y, which is 1, and the z derivative of z, which is also 1. And then I'm going to sum them together, and I get a constant divergence here of 3. All right, not too bad. Now for the divergence of r divided by its magnitude. Okay, so this is the unit radial field that points in the direction of this vector field r, because we're dividing r by its magnitude. So in component form, this thing is going to be x divided by r, y divided by r, and z divided by r. So if I take the divergence of this field here, okay, I'm going to need to apply the quotient rule, and I'm going to also incorporate the chain rule as I differentiate this quantity r. So let's go ahead and do that. So taking the x derivative of the I component, I'm going to get low d high. So it's going to be r times the x derivative of x, which is just 1. So r times 1, minus high, which is x, times d low. And that's just del r del x, and that's just x over r. And then I'm going to divide all of that by the square of what's below. So I'm going to get an r squared down here. And I'm going to get analogous calculations here for the y derivative of the j component and the z derivative of the k component. Okay, and so now to simplify this, well, first I'm going to, in each fraction, multiply top and bottom by r just to clear out this fraction, this division by r here. So that's going to give me r squared minus just x squared upstairs, and then I'm going to get an r cubed down here. And then likewise, I get r squared minus y squared over r cubed, and then r squared minus z squared over r cubed. So if I combine all of that, I'm going to wind up getting 3r squared minus the quantity x squared plus y squared plus z squared. But see, this is just r squared. So you get 3r squared minus r squared is 2r squared over r cubed, and that simplifies to 2 over r. All right, so a little more involved there, but still not horrible. Moving on to compute the divergence here of r divided by the square of its magnitude. Okay, pretty similar calculation there. You wind up with 3r squared minus 2 times this quantity, x squared plus y squared plus z squared, which is just r squared. So you get 3r squared minus 2r squared, which is just r squared. If you divide that by r to the fourth, you wind up getting 1 over r squared. All right, moving on here. When you have r divided by its magnitude cubed, okay, well, something interesting happens here. You wind up with 3r cubed minus 3r times that quantity, x squared plus y squared plus z squared, which is just r squared. So here you get 3r cubed minus 3r cubed, which is just 0. Okay, so in this case where the exponent on the magnitude there is 3, you wind up getting a divergence that's constant 0. All right, so then how about the fourth power? Well, pretty similar, but now you wind up getting 3r to the fourth minus 4r squared times r squared. So 3r to the fourth minus 4r to the fourth, which is minus r to the fourth, and then you're going to wind up dividing that by r to the eighth. And that simplifies to a negative 1 over r to the fourth. Okay, so just looking at the progression here, as we increase the exponent by 1, okay, if I think for the moment our radial distance r is just equal to 1, just for simplicity, okay, notice the divergence there would go from 3 down to 2, down to 1, to 0, and then we wind up with negative divergence. Okay, all right, so now let's go ahead and do the general calculation where I just have an exponent of p, and so pretty similar here. Okay, you wind up getting this expression right here, 3 minus this exponent p, all divided by r raised to the p power. Okay, so a couple big takeaways from all these calculations. The first thing I want to highlight is the fact that when p is equal to 3, this radial vector field, right, where you have r over the cube of its magnitude, this thing satisfies the inverse square law that we discussed back in section 15.1. And this takes special note here because a lot of forces in the universe satisfy this inverse square law, right? An example is, say, the gravitational force, right? And here, when P is 3, as we've computed, right, the divergence of this field is 0, right? This thing, in other words, is source-free on its domain, which is all of three-dimensional space, so all of R3, excluding the origin, right? Because at the origin, the radial distance there is 0, and so I have a division by 0 there. Okay, but this thing is source-free on its domain. Okay, so this is going to be a fact we are going to return to a little bit later on in the chapter. Okay, the other thing I want to point out here, just to try to get a little bit more of a physical intuition for why it is we're seeing things play out the way we are. So here I've plotted the radial vector field where right now the exponent p is just 0. Okay, so this is just xyz divided by its magnitude, in this case raised to the 0 power. So this is just the vector field r itself. Okay, and here I've just placed this little green ball, which is roughly about 1 unit away, the center is at least, from the origin here. And so when we're computing divergence, right, we're looking, we're ultimately interested in the net flux uh, through this ball, right? And so right now with p equal to 0, right, we note that as we move further away from the origin, the lengths of our radial vectors are increasing. Okay, so now as I enter into this ball, right, I'm going to get some inward flux, but then I'm going to get outward flux. And since the radial vectors are larger out here than they are in here, okay, there's going to be a greater outward contribution there than inward. And since our calculation for the divergence was constant 3 there, what that's saying is that the balance there between outward and inward is such that we're getting greater outward flux and it's constant. So if I move this ball to some other place in space, that same balance will be observed, right? That the outward flux will outweigh the inward flux, and that balance winds up being equal to a positive 3 for the divergence. Okay, so now what happens as I increase this exponent? Well, here, when p is 1, okay, this is the unit radial field, so all these blue vectors now have just length 1. Okay, so we're still going to get inward and outward contribution. Okay, but now since the vectors are all the same length, okay, the net outward flux, uh, it will ultimately still outweigh the inward flux, but the amount at which it's outweighing it will depend on how far I am away from the origin. Okay, because we got a calculation there for the divergence that was 2 divided by r, right, when p is equal to 1. So if I'm way far away from the origin, okay, I'm still going to get greater outward flux, but the difference between outward and inward is going to be relatively small when compared to when I'm, say, really close to the origin. There, the outward flux will greatly outweigh the inward flux. Okay, and a pretty similar story here when p is 2. Okay, except now, remember we got a divergence here that was equal to 1 divided by r. Okay, and so if I'm, say, looking at just when the radial distance r is 1, my divergence there would equal just 1, okay, as opposed to a divergence that would equal 2 when p was equal to 1. So there I'm just seeing that, yeah, I'm still going to get a net outward flux that is uh, positive. It's outweighing the inward flux, but it's just not quite to the same extent when the radial distance there is 1. Now, once you bump it up to 3, okay, this is sort of the sweet spot. Okay, sort of the Goldilocks effect. Uh, right here, okay, now the lengths of our vectors are shrinking as you move away from the origin, and they're doing it in such a way that the inward and outward flux, they perfectly balance each other out. And so the net flux there is 0. Okay, and that's happening anywhere I place this green ball in three-dimensional space, except at the origin itself. We have some domain issues there, right? But here, again, this is that perfect balance where the inward and outward flux counteract each other. Now, when you go up to, say, 4, now things are shrinking at such a fast rate as you move away from the origin. Now the inward flux takes over and your divergence is actually negative. Okay, so that's the physical intuition that we're getting here from this calculation. Okay, well, that's a good place to stop, and I will see you in the next video. Thanks so much.